I say I drop one, and then whatever you do extra credit, like if you do on your own, like you want to do the first 3 sections of chapter 6. The first 2 sections are not that tough, and then he has this little application in section 3. Do uniform approximation. There's not a lot of theory there.
It doesn't look like there's any problems out of section 6.1.
No, there's no problems out of section 6.1. So basically, 2 problem sets, the equivalent of 2 problem sets. He wants to write a short paper, maybe 3-4 pages or something like that. Do some examples, do some problems out of that business, and that's for extra credit. Roughly 25 points added to your homework grade. To make a wonderful homework grade or something like that. That's anybody can do that. I just would sort of like to know in advance what you're going to do.
But I could do the waveless thing.
You could do something like that. You said you wanted to do something related to section 410 maybe, or this chapter 5 is open. This chapter 11 is still open. Pretty much anything is open in this book other than what we've covered.
How would you know what homework sections?
You can do chapter 6 as well too if you want. Anybody can do. You can all do the same thing for extra. If you want to do 6.1 through 6.3, what he did is he looked at it and said, "That's a nice easy chunk. I can deal with that." He said, "I'll just do it." Okay.
Did he do like every problem? Or?
No. He's not going to do every problem. It's going to be up to you. He just writes up a nice little write-up about it. And if you want, if we wanted to, we could ask him to give a talk. But I said no. That's not necessary. Okay. You don't have to give a talk. You just write up, if you want to do, 6 problems of your choice and just write it up so that it just needs to be a little bit presentable, I think that's the whole point, is that it doesn't have to be given in class. It doesn't have to be, but I want it to be just, he was suggesting just a little bit different than just writing down some, notes on a paper. And saying, this is how I solve problem 1, 2, 3, and 4. So I'm not assigning him the problems. I'm saying it's yours to do as you wish. Okay? And then I'll grade it accordingly. But basically as an equivalent of a homework set. How did you do justice to it? Did you do 3 or 4 problems anyway? Okay? Plus give a nice presentation. Or give 3 or 4 examples. Do something. So I'm leaving it open. But I will grade it. And since it's extra, I'm not going to be real... as long as you did a halfway decent job, didn't just copy out of the book, like for 4 pages. It's like, well, I do a lot of copying when I'm doing, so the fact of the matter is you can't get something out of it as long as you go through it.
You have to go through it.
You have to go through it. So, I do plenty of copying when I write out these notes that I'm going to follow. Okay. So... and then I also do some problems, so that's the key. You want to be able to get through some problems. So
for the wavelets that I was going to do, there are no problems. That's the problem in that book. It's just theory. There are no exercises. There are no problems. So I just go through.
You'd have to find something. Yeah, you'll have to find something. But if you want to write up a short paper or something like that and present it.
It's like a nasty book.
Yeah, I don't like. I think Jorgensen, Palle Jorgensen, he does a lot of wavelet stuff. He wrote a book that probably has some exercises.
So. It's your choice, Joyce. It's got to be something presentable in some way, though, at least in paper or on the board. I would say if it is on the board, I would also like something in paper.
Well, that's what I thought of doing, because it didn't have problems. I thought I could present the theory, type up some nice notes for everybody, and then present it. So that would be more than just... I don't know if that's good enough or if you...
Yeah, as long as you can find a way to approach it so that you don't, this fits in the course reasonably. You have to find what a wavelet is, right?
Right.
That's going to take most of the time.
Dr. Phillips wanted me to do that. He thought the respaces was probably pretty applicable to functional analysis. He thought that would be a nice section to present. The only thing is that's in chapter 2, so I probably still have to present some chapter 1 stuff. Otherwise,
sounds like maybe it's too much. Why don't we bring this offline and discuss it after class or something? Because I don't know what it is, but I need to. If it's out of this book, I can, just say yes. Okay. If it's something else, maybe we need to look at it just a little bit, but I have to be able to grade it, So, why don't we continue with this discussion afterwards? But anyway, I'm just leaving that open. That's what he wants to do. Okay, that's the model. I think that works pretty well. The book there's lots of little sections we're not covering. You want to do something a little bit more associated with your research. That's fine. Okay, let's just talk about it a little bit. I think just getting to the definitions of wavelets, doing it nicely, and presenting a couple results, that relate at all, not even proving that much, would be, enough. Okay? So she's got a research topic. 1 homework set. The equivalent of work of 1 homework set. How much do you spend on that? Okay. Let's go on. Let's talk a little bit about weak convergence. Just because you need to be educated a little bit about the concept, and weak star convergence. So let's just talk about that. What is weak convergence? Okay. Somehow this is in your notes 10. Somehow I left mine at home, so I'm going to have to make it up again. But weak convergence. So let X be a norm space. Okay, and then I have a sequence X and a sequence in X converges weakly to X if when I apply an arbitrary linear functional, I get convergence to the corresponding functional applied to X. All right, if fxn goes to fx for every f in the dual bounded linear functionals. Okay. So obviously, if xn goes to x in norm, sometimes we call that strong convergence or norm convergence, then obviously you get the weak convergence, but the converse may not hold, as we'll see in an example. Obviously, if xn minus x goes to 0, that's convergence in norm, which is what we've been doing with the whole course, then converges weakly, and it's denoted xn with a little w over the arrow to x. Okay, if you get the norm convergence, then weak convergence follows. Simply by using norm inequality. Okay, fxn minus fx in absolute value less than or equal to the norm of f times the norm xn minus x. Okay. Okay. And if the norm goes to 0 and the norm of f is finite, which we're assuming here, okay, then this goes to 0. Okay. So the first thing is that you want to make sure this is a good definition, okay? And so you want to check that indeed the limit is unique. Lemma. And this is using one of the points of this is to use some of the tools we have. Let me see the number of this lemma. Okay. This lemma in section 4.8 is 4.8-3. I'm not going to go through all the lemmas in this section, so I'm only going to skip over 4.8 and 4.9 a little bit for your education and sign a couple problems. 4.8.3. The limit of x, a limit x, the weak limit. Assume xn goes weakly to x. Okay? The weak limit x is unique. Okay, it can't converge weakly to two different things. Well, maybe you could pretend that. You have your sequence, and maybe there's two different limits x and y. Maybe that would be possible. And then C, the important part, the sequence is bounded. in norm. And I guess B is each subsequences converge weakly to X, but that's trivial. B, X, and K goes weakly to X. All right, that's trivial. All right, because obviously if fxn goes to f of x, then fxnk goes to f of x by convergence of subsequences in the complex numbers. Okay. The sequence is bounded. Okay, how do you get these results? Let's try A. Okay. How would you get that? The limit is unique. Well, suppose there's two limits. Suppose fxn goes to f of x for all bounded linear functionals, and fxn goes also to f of y for all f in x prime. Okay, so that means that f of x equals f of y. So f of x equals f of y, or f of x minus y is equal to 0 for all f in x prime. Now, however, the functionals separate points. Okay, that was the corollary 4.3-4. That means that, but what we have is that 4.3-4 gives that the norm of x minus y is equal to the supremum over all functionals f of norm 1, f of x minus y, okay, in absolute value, okay, which is therefore equal to 0. Okay, since that's equal to, therefore the x minus y is equal to 0, and therefore x equals to y. So that's the uniqueness. Okay. So the point is that you can't get to them with different limits because the functionals separate points. We saw that actually we mentioned that as a homework exercise or something like that before. There was a homework exercise to that effect earlier. Lots of times he repeats himself, but that's good because you can remember these results. You have to see them 2 or 3 times usually to really remember. Okay? So that's what we're doing here. We're kind of going through this stuff so you remember. Okay? I know working with them more gives you more memory. But what about part C? The sequence xn is bounded. What do you think that's going to come from? Well, that's the trick is to say, okay, we had a previous result saying if I go to the second dual, then the canonical element of the second dual is defined by an element in the original space, has the same norm, okay, as the original element. Recall this for proof of C. Recall. For x in the norm space, we have g sub x in the second dual are defined by g sub x of f is equal to f of x. Okay, f belonging to the dual space. Okay. So in that way, you actually had that the original space was isometrically embedded into the second dual, because you have that g sub x, the norm, is equal to the norm of x. Okay. G sub x, where g sub x is this is the linear functional norm. Okay, is the linear functional on x prime. Okay. And this is just the norm in the original space. So this g sub x norm is equal to the supremum over all f g sub x of f f of norm 1, okay, f in x prime. But of course that's just equal to the supremum of f of x by its definition, norm f equals to 1, fn x prime, which we just said by this 434 was equal to the norm of x. Okay? So going this way. And then going back this way. Okay? This is by 4.3-4. This is by definition. And this is by definition. Okay? You understand what I'm doing here with this little diagram? I'm just recalling one of the results we had. That we actually have this is equal to that. Remember, this comes from the harmonic theorem, that I can actually evaluate the norm of x by looking at the supremum over all linear functionals of norm 1. Okay, so this is basically the harmonic theorem here. Okay. So I'm just recalling that. So therefore, basically, I can think of the norm of xn as the norm of one of these, a g sub xn. Okay. So that means I can think of xn as actually the norm of an operator or a functional. Okay. So that means I can bring in the uniform boundedness theorem. Okay, hopefully. But what the uniform boundedness theorem needs is a complete space. But luckily, x prime is automatically complete. So we're in. Okay, so let's see how that works. So that's kind of a lucky thing that happens. Okay, in some sense. So now I claim that I can apply the uniform boundedness theorem. All right. Okay, so for proof of C. So proof of C continued. Idea, I use uniform boundedness theorem. Which we proved last time. What does that require? It requires a Banach space. Okay? To the sequence G sub n in x double prime. Okay, so that means that G sub n is mapping x prime to the complex number say, all right, where G sub n of f is equal to f of xn. Okay, I just put G sub n instead of G sub x sub n. I don't want to have to go through all that. Okay, just where. So now I have a sequence of operators on a Banach space. Okay? This is my Banach space. They're linear functionals, not operators per se, but okay. So Gn is mapping x prime to C, where Gn of f is equal to f of xn. Okay. I need to check the hypothesis of the uniform boundedness then. What is that? That means if I fix an element in the domain, and I take the sup over all n, I get a number that depends only on that element. Then I get a finite number. Okay? The hypothesis is that, so check hypothesis, the other hypothesis, besides the fact that I have a Banach space, and that is that the supremum over all n of G sub n of f, okay, is less than or equal to a constant dependent only on f, which depends on which, well, there's no other constants to be anyway, which is less than or equal to c less than infinity, c sub f. Okay? Is that true? Well, G sub n of f is f of xn. I'm taking the sup on n. F is a fixed number now. Okay? I mean, it's a fixed functional. Okay? F is fixed in this computation. Maybe you should look up the uniform boundedness theorem. 473. Okay? So that you'll understand what I'm talking about. 473, which is what we did last time. Basically, it said, suppose I have a sequence of bounded linear operators, and suppose that if I take the supremum of the norms of Tn of x, that's finite. Okay? That's the assumption. Then, as long as I had a Banach space to begin with, then actually the supremum of the norms is finite. Okay? So for each fixed element of the domain, I need the supremum of the norms to be finite. Here that just means the absolute value, since Gn is a linear functional on the space of linear functionals. Well, this becomes, in terms of our definition, f of xn, the sup over all n, is finite. Is that true? Well, I'm fixing, there's a finite number, so xn is my given sequence. Okay, f is a given bounded linear functional. Is that finite? Well, yeah, because I am assuming that this sequence fxn converges. A convergent sequence in C and the complex numbers is bounded. Convergent sequences are bounded. True, because convergent sequences are bounded. Remember that from real analysis? Sequences of complex numbers, of real numbers or complex numbers, are bounded. They actually always, convergent sequences in the norm are always bounded, period. Okay? By the definition. Okay? As long as I'm in a norm space, so I can talk about bounded. Even in a metric space, you can make an appropriate sense of bounded. Okay? I think that was given in chapter 1, in fact. So any convergent sequence is bounded. Okay? So the hypothesis holds. Therefore, what I have is that by 473, the uniform boundedness theorem, we have that the supremum of the norms is finite. But that's just the same thing as the supremum of the norms of the x sub n's is finite, because that the norm of Gn is the norm of xn. Here, we have that. Okay? Okay, so therefore C is, since norm Gn equals norm xn. Okay? So I'm done. Okay, so C is proved. Okay. QED. Okay. So just kind of a little thing to remind you of what we were doing, what we've done so far in this course, so you can get these little ditties come falling out. Okay? Because I'm calling them little ditty at this point because I'm not going to do a whole lot with this business. I think one of your problems I assigned, I asked you to deal with the lim-inf. Does anybody not know what the lim-inf is? You don't know what the lim-inf is. Okay. So for homework problem 4.8, number 4, you need something called the lim-inf. Limit inferior of a sequence of real numbers, a(n). N goes to infinity. What the heck is that? Limit inferior, or in French, or Latin, whatever it is. Okay. Okay, this is the way I remember it. It's just got a fancy name. Limes inferior. Okay. Limit inferior or lim-inf. Okay. Okay. What does it mean if I have a sequence of real numbers, that a(n) equals a sequence of real numbers? You should all know this somewhere in your career. So there's a little bit of filling in some gaps, perhaps, with this section. Okay? What is the limit inferior? Anybody remember that stuff? Or lim-sup and lim-inf? If you have a sequence, it's the smallest possible limit point. That's one way to say it. Okay? So it's the smallest possible limit point. Lim-inf is limit if an equals smallest limit point possible, including minus infinity. Including minus infinity if an is not bounded below. So if you can just keep going down along some subsequence, so basically you're looking at subsequential limits, okay, and it's the smallest possible subsequential limit. Well, actually, it's not a limit point. I shouldn't call it limit point. Smallest subsequential limit possible. Because the limit point is not quite the same. Because if I have 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1, there's no limit point to the set 1 and minus 1. But there are subsequential limits, namely minus 1 is a subsequential limit. So that's the limit. Okay, the largest possible subsequential limit is 1 in that case. 1 minus 1, including limit possible, including minus infinity if the limit is not. Okay, so let's put it that way. The way it's officially defined is this. What you do is you take, how do you know this thing always exists? What you do is you take, if you take the infimum of a sub n of a sub k for k greater than or equal to n, that's some number, right? That's, I call that capital A sub n equals the infimum of all those elements, okay? So if I'm thinking of 1 minus 1, 1 minus 1, that's just the infimum of 1 and minus 1, which is minus 1. Okay, and now that's, as n increases, an goes up, okay? At least it doesn't go down, okay? That is, it's non-decreasing, okay? So, and of course, it's and then the lim inf is defined to be lim inf a sub n goes to infinity, equals the limit as n goes to infinity of this capital A sub n. Okay? So I don't know if that's helping you much. But basically what happens is if an is less or equal to bn, you get some obvious things. If an is less or equal to bn, then the lim inf of an is less or equal to the lim inf of bn. These lim infs always exist, though they might be minus infinity or plus infinity. Plus infinity is also possible. If you have a sequence going to plus infinity, you can get plus infinity. So, for example, an equals to n gives that the limit inferior of an is equal to infinity. Okay? So you can get plus infinity. Obviously, you can get. We also said you can get minus infinity. Okay. So the bar is just to say it's the smallest possible subsequential limit. Okay. Then you have the largest possible subsequential limit. That's the lim sup. So as long as you allow plus and minus infinities, these always exist. That's the nice thing about lim inf, lim sup, is whereas limits don't always exist, these always do. So you can play with them sometimes. And I don't know if that's going to help very much for the summer problem. Maybe I'll have to make it extra credit if it's giving you too much trouble. But I think this is the only one you're going to need. This is the only property you're going to need. I said it's 4.8, number 4. Okay, the problem is to show that that the lim inf of xn is less than or equal to, let's see, if xn goes weakly to x naught, I think the problem was then the lim inf is greater than or equal to the norm of x naught. Okay, so if show in 4.8 number 4 show if xn goes weakly to x naught, then the limit inferior of the norm of xn is greater than or equal to the norm of x naught. N goes to infinity. And notice that that's trivial when x naught is equal to 0, because you have a non-negative sequence, okay, in that case. So if x naught is equal to 0, then this is trivial. And if x naught is not equal to 0, it says to what theorem to use. Okay, so you shouldn't have too much trouble. So, you know, if an was lesser than equal to bn, the limit is lesser than the limit here, and if an was greater than or equal to bn, you'd also have the limit of an was greater than or equal to the limit of bn. You just get the natural inequalities, because that's just termwise. Because if this is termwise, then of course the infimum has to correspondingly be termwise, and you do eventually get these limits as limits. So it's not very hard to prove. Okay? Using the definitions. So things involving inequalities work with these lim nth and lim sup. Questions about this? I know it's a real quick development, lim nth, lim sup, but other than that, the problem's pretty easy. Okay. Okay? This is a one step. It tells you what to do. Okay. So try that one. I know you're going to hate lim nth, lim sup.
Did we cover that in our analysis class?
They did not cover it in 431. Did not cover it in 431, but it's in 341. 341 usually. Okay. And I usually leave it as a topic in 431. But I usually introduce it because it just, you see it so many places, you say, well, what the heck is that stupid
Yeah, I saw it
thing?
in Roydland, didn't know what it meant.
Okay, yeah. Most of you people have assumed you've seen it at some point. And they just don't want to take time to spend a page on recalling it. The lower bar, yeah. You can see there's also lim nth.
Yeah.
Okay, lim nth. an equals this. Yeah, there's the two notations. Okay, what is weak star convergence? Let me just say what that is. And you also have a homework with that. Weak star convergence. So then we talk about a sequence of linear functionals converging. Okay. Okay. So this is in the next section, 4.9. I'm not going to cover all the other stuff in this section. It's just a lot of talk. Okay, it's too much. So what's weak star convergence? This is 4.94 part B. Okay. Fn, a sequence in the dual space, X prime, okay, converges in the weak star sense to F in X prime if Fn of X goes to F of X for all X in the original space. Okay. So now it's the sequence of functionals converging pointwise. Okay. So that's not the same thing as strong convergence. That would be strong convergence means that the norm of the difference is going to 0. This just means which would be which is a uniform convergence. This is a pointwise convergence idea. You've seen that in when you see continuous uniform, the study of continuous functions and uniform convergence versus pointwise convergence, all that kind of stuff is exactly the same notation, right? A function at X goes to F of X. Only problem is here that X is a vector in a larger vector space than you were working with before. Before it was X on the unit interval. Now it's X or X on the line. Now it's X in a vector space, in a norm space. Okay. Okay, so that's the weak star, and then you write Fn and with a W star for the arrow, denoted. Denote this. Fn goes weak star to F. Okay? That's all you're going to do. Okay. And then we have the main theorem here, 4.9-7, which gets us into the new notes. Maybe I should give you those. Okay. I want to talk a little bit about 4.11. Not too much there either. So I'm skipping through the end of the chapter to get to the main results at the end, so that we can go on. I know you say, go on to what? Well, yeah, quantum mechanics. But I don't want to get mired in this stuff forever, but I want to get to the main theorems this week. Open mapping theorem and the closed graph theorem. We've got to have those because those get applied a lot in the later chapters. Okay. And without in this chapter we're applying the Hahn-Banach theorem mostly. Okay. What we just did with that corollary of the Hahn-Banach theorem, 4.3-4, in order to get the properties. Okay, there's another one where we're going to do this. Corollary 4.9-7. A sequence of bounded linear functionals on a Banach space is weak star convergent to a bounded linear functional F if and only if. Okay, so this is going to be an if and only if for weak star convergence. Fn in X prime, a sequence in X prime, given this, for a Banach space X, converges in the weak star sense or is weak star convergent. You can use it as a verb or as a noun. Okay, to a bounded linear functional F on X if and only if the following two conditions hold. A is that you should have a bounded sequence. Fn is a bounded sequence of reals. The norms are bounded. That looked necessary from what we did before. Just thinking about it, what we did before, we said that the norms, for the weak convergence, the norm of the xn's had to be bounded. Okay, if they were weak convergent. So it looks like this is the right thing. Well, we'll just check that. And that's going to hold also by the uniform boundedness theorem. Okay, in this case. So that's going to be necessary by the uniform boundedness theorem. Okay, and B, what I need is that Fn of X, the sequence, is a Cauchy sequence of complex numbers, of course, or real numbers if I'm in a real Banach space, but a Cauchy sequence in the ordinary field for every X. I don't have to check it for every X whatever, but for every X in a total subset. M of X. So I need to check there's a Cauchy sequence in a dense set, basically. Okay? Why? Because, well, what does it mean for a total subset? What's the definition of total? Remember that was like a total subset is a set such that if I take the span of that and then take the closure of the span, I get all of X. Means the span of M closure equals x. So I've got something that may not have a linear structure itself, but when I do make it into a linear structure by taking the span, then that's dense. Okay? Okay. Alright, so I have to have Cauchy on a dense subset, roughly speaking. Okay? Okay, why are A and B necessary? And then let's show the sufficiency. The necessity, let's see how that goes. Why is A necessary? Let's check that. Because I'm on a Banach space now. Remember before when I used the uniform boundedness theorem, I had to use the fact that the dual of a norm space was a Banach space. Now I'm going to use the fact that X itself is a Banach space. Okay. To get A. Alright? What you have is that Fn goes weak star. A is necessary. So what I'm saying is this. If and only if this. So I'm going to the proof this direction, therefore. Okay, I'm showing that if I have the weak star convergence, then A is necessary. Fn goes weak star to F means Fn of x goes to f of x for all x and x. Okay? And in particular, therefore for each fixed x, you have that the supremum Fn of x n greater than or equal to 1 is finite. Okay? Because if you have convergence, then you have a bounded sequence, as before. Hence, by 473, as before, only a little bit more directly this time, since capital X is complete now, okay, the supremum of the norms is finite. Okay? Uniform boundedness theorem. Okay? And therefore this A holds. There's a bounded sequence of reals. In other words, the supremum of the norms is finite. Okay, what about B? Does that necessarily hold? Well, it says that should be a Cauchy sequence. Well, we assume that Fn of x is convergent for each x, and therefore in particular is Cauchy for each x in a whole space x. So B holds with m equals x. Okay? Also, B holds with m equals x, since convergence of Fn of x is a sequence of scalars, okay, implies that Fn of x is Cauchy. Okay? So B holds. So those are necessary conditions. Now let's show the sufficient. Let's take the reverse implication now and show A and B implies weak star convergence. Sometimes just call it weak W star convergence. Okay? Is that okay? Weak star or W star. I'll put weak star because the you can't call it weak convergence because we already talked about weak convergence, so we'll call it weak star. It's easier than writing weak prime convergence, I guess. So, okay. So how do you do this? This is kind of interesting. All right. Now suppose A and B hold. I need to check that this condition holds that indeed Fn of x goes to f of x for all x. This is check the condition. Okay. All right. So I need to check that condition. Let x belong to x. Okay. by A, okay, what do I have first is there exists a constant C less than infinity, so that the norm of Fn is less than or equal to C for all n. Okay, so I got bounded norm. I've bounded all my norms. Okay. Okay. And now I need that C. Since M is total, there exists a Y in the span of M. By the density of the span of M, okay, there's a Y so that X minus Y in norm is less than epsilon over 3C. Okay. Okay. And now what can I do with that? Now the rest looks like an analysis proof. Okay. A linear combination of quotient by B, since Y is a linear combination of an elements in M, okay, it's a finite linear combination. This is the only complication here, because instead of saying a dense subspace, I said a total subset. Okay, so I have to worry about finite linear combinations and so on. But a finite linear combination of Cauchy sequences is again Cauchy. Okay, so that's of elements of M, then Fn of Y is a Cauchy sequence. A finite linear combination of Cauchy sequences is again a Cauchy sequence. Okay. Okay, now what I want to do is show that Fn of X is a Cauchy sequence. Okay. So all I'm going to do is I need to show that this is a Cauchy sequence. Okay. Okay. Oh, yeah. So I need to show that there really is some linear functional that does the job. Okay. So to show Fn of X is Cauchy. Okay. That sequence. All right, and then I'm just going to define I'm going to define f by taking the limit of that and call that f of x. Then it's going to follow that's actually a linear function. Okay. Well, the linearity will be trivial because Fn are linear. Okay. And the fact that its norm is finite is going to fall out in the wash here. Okay. So what I have is that I have Fn of x minus Fm of x. How could I write that? This is going to be a triangle inequality idea where you use the Fn of x and Fn of y, and then you use this business. So you have this is less than or equal to Fn of x minus Fn of y plus Fn of y minus Fm of y, which I already know how to control because Fn of y is Cauchy, plus Fm of y minus Fm of x. The first and the third terms I'm going to bound using this x minus y less than epsilon over 3c, and the fact that the norms are all less than or equal to c. Okay, so that the first term is therefore less than or equal to the norm of Fn times the norm of x minus y, and then I have a third term the same thing, plus the norm of Fm times x minus y. And then the middle term is Fn of y minus Fm of y. I'll just leave that as it stands because I'm going to use the epsilon argument. Okay? So this is less than or equal to according to that, this is at most c, this is at most c, there's an epsilon over 3c for x minus y, so this is 2/3 epsilon plus fn of y minus fm of y. Okay. Therefore, since fn of y is Cauchy, well, just put sense, not therefore sense. Since fn of y is Cauchy, there exists a capital N, so that fn of this third term minus fm of y is less than epsilon over 3 if little n and little m are greater than capital N. Okay? Hence, if little n and little m are greater than capital N, then fn of x minus fm of x is less than epsilon. Okay? So fn of x is Cauchy in the scalar field. Okay? The x was fixed. Alright? So now what he's going to do is define f of x equals the limit fn of x that exists now and goes to infinity. Okay? It exists by above. Okay? And it's linear. F is linear. Since fn is linear for each n, what you're going to do is you're going to use the limit terms. Fn of x plus fn y is equal to fn x plus y equals f of x plus y in the limit. So it's just the limit theorem. And what about norm inequality? Well, I have that the norm of f, let's see, the norm is continuous. Therefore, the absolute value of f of x is equal to the limit of the absolute value of fn of x. N goes to infinity. Absolute value is a continuous function. Okay, which is therefore less than or equal to c times the norm of x, okay? Because this quantity itself, underneath the limit sign, is less than or equal to c times the norm of x, okay? Therefore, f is in x prime as required. And I guess I didn't show unicity here, that once I do have weak star limit, then I would have a unique limit. Let's see if that's something trivial. I don't even know if he does bother with it to prove uniqueness. How would you prove uniqueness? If I had fn going to f and fn going to g, then g of x equals f of x for every x. Well, then that's trivial, because then by definition it's the same functional. Okay? Okay. In other words, the uniqueness comes from the definition. If I have fn of x fn going to f and fn going to g, then g of x equals f of x for all x and x. That means they just have the same functional. The limit is unique by definition. I don't have to do any extra work. All right? Yeah. All right? So that's the proof of that lemma. We'll bring that in later. Well, actually, I want to talk a little bit about. Maybe I can just talk about this and sort of cover this numerical integration idea. It's somewhat interesting, but it takes us a little bit off the track. But I thought I'd mention it at least. Okay. For those people who take numerical analysis, at least they'll know something. Okay. But I've lost my numerical analysis book, so I couldn't give all the references that I wanted to. The Simpson's rule and trapezoid rule, you all remember those things from calculus, right? Midpoint rule, what have you. How do you numerically integrate something? But then there are other kind of ideas. Okay? And some of those are used, in fact, in Simpson's rule. But And he kind of takes us into a theorem that it seems to be disjointed in this approach from the trapezoid and Simpson's rule, but that's all he assigns in the problems, is then he talks about trapezoidal rule and Simpson's rule. So I'm a little bit disappointed. He doesn't connect his main theorem here with what he's got in his problems. Okay? So I need to point that out. That he kind of takes you with a theorem, and then when you actually get to the problems, then it doesn't have anything to do with the theorem at all. Okay? Per se, except building blocks that you would do if you were going to actually study something in numerical analysis. Okay, so let me describe the application. Okay, and then maybe I can make a couple more comments next time if I can find a numerical analysis book. Okay. So here's application to numerical integration. I haven't been disappointed hardly at all with this book, though. Let me say this. I think this is the most wonderful book I've ever seen, because he can actually write a book that you can completely understand without being super hard. This book is not super hard ever. He never gets hard. I can't believe it. He never gets hard. Okay? And yet he continues to amass momentum and covers his whole subject, including quantum mechanics at the end. I mean, it's impressive. Impressive. So, I don't know anybody who could write a book that well. In terms of just if you wanted to self-learn or self-study or do as we're doing, having to learn this course in a very small class, me for the first time. So, I can't say enough about this book. So let x equal C01. Okay. With real values, let's say. Let's just deal with the real case. Okay? And define a numerical integration scheme. For example, think midpoint rule or trapezoidal rule. Midpoint rule, trapezoidal rule, or Simpson's rule, and beyond. Okay. Okay. To calculate the following linear functional: f of x equals integral 0 to 1 x of t dt. Just calculate the integral. That is a linear functional, is it not? Okay. So what I want to do is calculate that as follows. Our general scheme is simply just to write fn of x equals summation k goes from 0 to n alpha k super n. So I'm going to write it alpha k super n of x of tk super n. So what I'm going to have is I'm going to have some nodes, so-called. Usually you just think about them as the partition points. 0 less than or equal to t0 super n, less than t1 super n, less than so on, less than t sub n super n, less than or equal to 1. You don't actually have to use the endpoints if you don't want to. Okay, so the midpoints, for example, of the partition intervals would be our nodes where we're going to calculate x, and these are going to be some kind of scalar coefficients. Okay, like maybe they're all 1 over n in the case of the midpoint rule or something like that. Okay, you just take the average of the function values. Okay, at the midpoints of the partition intervals. So, for example, what would I have? He does something involving the length of the partition, but if I took, for example, n equal to 4 and T0 equal to 1/8, T1 equal to 3/8, T2 equal to 5/8, and T3. Let's see, do I have too many things here? N equal to 4. Why did I do n equal to 5. Okay. Why do I have so many? Here he's want n equal to 3, the way he's got this thing. I don't like the way he did that either. Okay. Okay. J3 equal to 7/8. Okay, so that's with the midpoint rule. Because, okay. Then I've got, then I'll take Fn, this is the midpoint rule. I'll take Fn of x is equal to 1/4 times times x of 1/8 plus 1/4 x at 3/8 plus 1/4 x at 5/8 plus 1/4 x at 7/8. Let's draw a picture, make sure this is correct. Okay, 1, 2, 3, 4, 0, 1/4, 2/4, 3/4, 4/4, and I'm saying I'm taking the midpoints of these subintervals. Okay. I'm multiplying the height of the function by the width of the interval, which is 1/4. Since I'm working on the unit interval, I just have it this way. And so then I'm getting these rectangles as the areas of these rectangles as the summands here. Okay. So I have the areas of 4 rectangles that I'm adding there. Okay? To approximate the integral. Okay. So apparently his scheme, you know, with the n, he's got n plus 1 nodes that I don't like. But anyway, that's what he's done. Let's see that, 411, but that's because he's doing something a little bit different. Okay? Okay. So why is he going to, so this is a general scheme there, just always something like that. Now, he's going to introduce this idea that I want that in order to apply this 4.9-7 we just proved, he's going to introduce this idea that I should have that if I take polynomials, that I should actually have Fn of x equal to f of x. Okay? That doesn't seem possible at all with this midpoint method, right? If I take x squared or x cubed or x to the 4th, I'm not going to get, or t to the 4th, I should call this t. This is x of t. If I take x of t equals to t squared, here's t, and then there's t squared, and then there's t cubed, right? And so on. If I take these functions, t squared, t cubed, and this is t, and I apply the midpoint rule, okay, I guess they all go through 1. What happened here? Okay. Like this. Okay. T squared, t cubed. And if I take all these functions and I apply the midpoint rule to each of them, the midpoint rule is not going to evaluate the integral exactly. Right? It's only going to do it for the linear one. So what he's going to do is he's going to say, well, we have so many parameters here. Okay? We have these nodes and we have these coefficients. We have so many parameters. 2n plus 2 parameters. Okay? So what I'm going to do is I'm going to force you to I want to make a unique solution. So what I'm going to do is I'm going to fix my nodes. Okay, so they're not going to be parameters anymore. Well, they won't be after I fix them. And then I'm going to try to figure out the alphas so that Fn of x is equal to f of x for all x equals t to the 0, t to the 1, t to the 2, and so on up to t to the n minus 1. So, okay, one method that the author produces, which he calls requirement 411-2, is to make Fn of t to the j equals f of t to the j, okay, for j equals 0, 1, up to n minus 1. I think that's what he does. Let's see about that. Okay, I'm not going to have time to finish that today. J equals 0 to n. I'm sorry. Okay. So this gives us certain requirements on the coefficients. And one can argue, which I do in these notes using a Vandermonde determinant, that indeed, as long as these t's are distinct, okay, you can find the alphas uniquely that does the job. Okay? So that's not the midpoint rule. Okay, that's not the trapezoidal rule, that's not Simpson's rule. And so when he says, what are the nodes? Okay, they're these. But do they have anything to do with what he required here? No. Okay. You understand what I'm saying? Yeah. Some of the ideas, to actually generate Simpson's rule, you can take the case n equals to 2 here, I guess, and use the Vandermonde determinant to actually calculate, all right, what the Simpson's rule should be. Okay. So you can use some of the ideas, but this is a little bit different direction. Okay. So what I did is I worked it out for one of the lower cases, and actually came out with all the dang coefficients by working out row reduction. Oh, it looks like these notes got out of order. Did they? No, this is okay. What I did is I took I took 5 sample points, I guess. So n equals 4. Okay. Which corresponds to 5 sample points. Okay. Because that's the way he's defining this thing. Okay. And I took the case. So solve requirement 4.11-2. What he does, he says, give me my nodes. What I'm going to do is just take the endpoints of the same interval here. Okay? So I'm going to take with n equal to 4. Okay. And with t0 equal to 0, t1 is equal to 1/4, t2 is equal to 2/4, t3 is equal to 3/4, and t4 is equal to 4/4. So I'm going to sample the function at 5 points. 1, 2, 3, 4, 5. The endpoints, not the midpoints now. Okay? So I'm going to have what I want to happen is that I'm going to have 5 equations, because I'm going to want n of f sub 4 of t to the 0. I want that to equal f of t to the 0 equals the integral of 1 dt, 0 to 1 equals to 1. I want f for t to the 1 equals f of t to the 1 equals the integral 0 to 1 of t dt equals a half. You can calculate that. I want f sub 4 of t squared to equal f of t squared equal integral 0 to 1 t squared dt equals a third. So whatever these coefficients are when I plug them in there, I want f sub 4 of t cubed equal to a fourth, and I want f sub 4 of t to the 4th equal to a fifth. So what I'm actually going to get if I write down this system, basically, which is the requirement that he's going to ask us to do, okay, then what I'm going to get is some equations, 5 equations and 5 unknowns. The 5 unknowns are the 5 alphas. So alpha 0, alpha 1, alpha 2, alpha 3, and alpha 4. I'm eliminating the superscript n for the time being, okay, because I'm going to have to recalculate every time I give you a new, at level n, and recalculate a new scheme. Okay, so you can see how it might not be a very convenient scheme that I'm introducing here for recursive development. Okay, there's too many equations to solve. But this is at least so you can see how it goes off into a different subject. Why trapezoid rule and midpoint rule is really much better. There is a theorem here. Okay, there is a theorem. And that theorem is that as long as you require this, as long as you do this requirement, and I'll just tell you what I get. You can go through the calculations in the notes. What I found was alpha 0, alpha 1, alpha 2, alpha 3, and alpha 4. If you go through these equations, okay, because you get 5 equations and 5 unknowns, what are they? You actually have to compute. You have to, let's say for the 5th one, what are you saying? Alpha 0 times 0 to the 4th plus alpha 1 times 1/4 to the 4th plus alpha 2 times 2/4 to the 4th plus alpha 3 times 3/4 to the 4th, because these are the heights of the t to the 4th curve, right? To the 4th plus alpha 4 times 4/4 to the 4th. That should equal a 5th for my alphas. That's one equation, okay? But they also have 4 others, okay, including alpha. For the 0th equation, it's alpha 0 plus alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 is equal to 1. The integral of a constant is 1, and that's just the sum of the coefficients. So the coefficients should add to 1, just like they did in the midpoint rule, okay? So what they actually come out to be is 1 over 180. There was a nice pattern, 1464. I didn't look in a book to see why this pattern came out. Okay, I just calculated the dang thing. Okay, and the coefficients do add up to 1. That looks good, and there's a nice pattern, which is good. Okay, so then that gives you something. Okay, that gives you an approximation of the integral. What his theorem is that that this convergence scheme under this requirement 411-2, which means that I have to recalculate at each level n to get a new fn of x, right? So for n equals 5 or 6, I'd have to recalculate the coefficients and so on, so that I get a sequence of linear functionals, right? It's a difference. X is the one function, whatever it is. It's a continuous function, okay? And then I would apply that functional, so it actually doesn't look the same from one. In other words, not only are the coefficients changing, but the nodes are increasing and so on too, right? So they're not fixed either. So the alphas aren't fixed, the t's aren't fixed. But I get a sequence of linear functionals, and that's going to converge in the weak star sense. Okay, if and only if the sum absolute values of these things are bounded. Okay, so and that follows exactly. So the theorem is that is 411.3. I guess we ran over now, way over. Okay, Fn goes to F. Fn of x goes to f of x under 411.2. If and only if the sum alpha k super n in absolute value, well, absolute value is here, is less than or equal to c. K goes from 0 to n for all n. Okay, that's the theorem, and that follows exactly from 49-7. And what's happening here, where I chose the nodes nicely, it turns out all the alphas are positive. So as long as the sum of the alphas remain bounded, here they were all, the sum was equal to 1. Okay? Then you actually get convergence. So in this case, where I actually do take the endpoints of uniform partition and solve out, I'll get something that gives me a uniform, that gives me the convergence scheme. Is it any good? I don't know. Okay. Is it any good? Because I don't have, in trapezoidal rule, Simpson's rule, you always get this convergence rate. All we're saying is it converges. Okay? So it does touch on this other subject, numerical integration. I think we'll leave it at that. Okay? Sorry. Sorry. Yeah, you all have to go, and we went over time.